Researchers in the US have begun building a new particle detector that they hope will help find an answer to a very big question.
Yeah, we're studying a fundamental particle known as neutrino.
Maybe one or two neutrinos interact sometimes.
For years, scientists believed neutrinos were harmless, ghost particles drifting through flesh, stone, and stars without leaving a mark. But now, the machines built to study them are detecting something they were never designed to find. Space itself is warping in their presence. Timings are breaking, signals are twisting, entire detectors are whispering the same warning. Something is wrong. These particles were supposed to be spectators of the universe. Instead, they're behaving like saboteurs. If ghost particles can bend space, what else can they do? And why is every physicist on Earth suddenly terrified to find out? The universe of ghosts. If you could freeze the universe for a moment, silence every star, halt every galaxy, you would still feel movement. Not through sound, not through light, but through something deeper and quieter. A river of invisible particles, neutrinos, streams through your body by the trillions every second. Gravitational waves stretch and squeeze space itself as they roll across the cosmos. Neutron stars, compressed remnants of dead suns, spin so violently that a teaspoon of their material outweighs a mountain. And in the darkness between galaxies, black holes twist space-time into impossible geometries. This is the hidden universe, a universe built not from the things we see, but from the signals we almost never notice. Neutrinos, sometimes called the ghost particles, were never meant to be easy. They have no electrical charge, almost no mass, and interact with matter so reluctantly that a wall of solid lead, a light year thick, would barely slow them. Yet these same particles hold one of the most important clues to why we exist at all. Their strange behavior, flipping identities mid-flight, may explain why matter survived the early universe instead of being annihilated by antimatter. Elsewhere in the cosmos, gravitational waves ripple relentlessly. First predicted in the early 20th century, they remained theoretical until detectors finally caught them in the year 2015. They revealed something astonishing. The universe is constantly trembling from black hole collisions, neutron-star mergers, and cosmic catastrophes that happened millions or billions of years ago. These vibrations are not just noise, they are information, stories encoded in the fabric of reality. And then there are the neutron stars themselves, the densest visible objects in the universe, the leftovers of massive stellar explosions. Their magnetic fields are so intense they can warp atomic structures. Their rotations are so stable they rival atomic clocks. When two neutron stars collide, they produce a kilonova, a burst of light and gravitational waves that forges heavy elements like gold and platinum. Every ring on your finger, every piece of jewelry ever made likely began as debris from an ancient neutron star collision. Yet, for all their violence, these cosmic phenomena remain almost entirely silent. They rarely emit visible light. They do not behave like ordinary matter, and they leave behind signals so faint that only the most extraordinary instruments can detect them. That is why modern physics has entered the era of multi-messenger astronomy, a discipline that listens to the universe through many channels at once. Light, neutrinos, gravitational waves, high-energy particles. Each messenger carries a different version of the cosmic story, and only by combining them can we understand what the universe is truly trying to say. Consider what happens when a distant star collapses. Photons may be scattered and absorbed by gas clouds on the way to Earth, blurring the event beyond recognition. But neutrinos, indifferent to obstacles, travel straight through the star, straight through galaxies, straight through us. Gravitational waves stretch space-time itself, offering a second perspective on the same catastrophe. Together, they paint a picture no single instrument could produce alone. This is why neutrino observatories are buried deep in Antarctic ice. It is why gravitational wave detectors fire lasers across kilometers of vacuum to measure distortions smaller than a proton. It is why long baseline experiments fire neutrino beams across entire continents. The universe does not easily reveal its secrets, but when it does, the revelations change everything. The ghost particles that flow through you right now may hold the key to why matter exists. The gravitational waves humming through space-time may tell us how galaxies formed and evolved. The collisions of neutron stars may explain how the periodic table itself was assembled. And the behavior of rotating black holes may expose the cracks in our most sacred physical theories. We are entering a new era, one in which invisible events guide our understanding more than the visible ones. The brightest stars are no longer our best informants. The universe now speaks in whispers, and for the first time in history, we are learning how to listen. When physics faced an impossible choice. In the early decades of the 20th century, physics stood on a fragile pedestal of triumph. Quantum mechanics was reshaping our understanding of atoms, while relativity had rewritten the laws of space and time. But beneath this confidence lurked a quiet crisis, one so severe that it threatened the foundation of the most sacred principle in science, the conservation of energy. The problem revealed itself through a process called beta decay, a transformation occurring within unstable atomic nuclei. Researchers expected that when a nucleus emitted an electron, the energy released would match perfectly with the energy measured. But as the experiments accumulated, something disturbing surfaced. The electrons carried away unpredictable amounts of energy, sometimes less than expected, sometimes far less. It was as if energy itself was vanishing into thin air. That possibility, energy disappearing, was unthinkable. The law of conservation had guided physics since Newton. To abandon it meant tearing down everything. Physicists were cornered. On one side was the idea that the universe's bookkeeping was flawed, that nature occasionally created or destroyed energy without explanation. On the other side was an equally unsettling alternative. Some invisible agent was stealing energy, slipping away undetected. Enter Wolfgang Pauli. Pauli, one of the sharpest minds of the 20th century, drafted a now famous letter in December of 2030, addressing colleagues with a blend of humor and urgency. Beneath the playful introduction was a clear sense of alarm. Pauli suggested the existence of a completely new particle, one that filled the energy gap without violating the laws of physics. This proposed entity had to be unlike any particle currently known. It needed to carry no electrical charge, possess almost no mass, and interact so weakly with matter that it could move through solid walls, entire planets, or laboratory detectors without leaving even a faint trace. It was a bold, almost desperate attempt to preserve the structure of physics. Privately, Pauli acknowledged how unsatisfying this solution felt. The new particle seemed too elusive, too ghost-like. He worried that such a thing might exist only in theory, forever beyond human reach. Yet without it, the equations simply refused to make sense. The particle would eventually be named the neutrino, the little neutral one, a simple label for something with far-reaching consequences. Enrico Fermi constructed the first theoretical framework around it and attempted to publish the idea in the year 2034, only to be dismissed by reviewers who felt the concept stretched credibility too far. Inventing an undetectable particle seemed like an act of imagination rather than science. Still, the missing energy in beta decay refused to go away. The anomaly continued to taunt physicists, acting exactly as if an invisible particle were carrying energy off into the dark. Either nature was breaking its own rules, or Pauli's phantom was real. For years, neutrinos survived only as mathematical whispers. No instrument could detect them. No experiment could prove they were more than theoretical fiction. They existed in equations, but nowhere else. Worse, if neutrinos did exist, they were fundamentally unlike anything in the known universe. They carried no charge. They seemed to have no mass. They interacted so weakly with matter that billions could flow through a human body every second without producing a single observable effect. Detecting them appeared hopeless. By the late 1940s and early 1950s, the scientific tension was reaching its limit. Physicists needed the neutrino, but the neutrino refused to show itself. The particle had become a paradox, essential on paper, absent in reality. Then everything changed. Two bold researchers, Frederick Rines and Clyde Cowan, believed that detection was possible, not with better versions of existing experiments, but with a completely new strategy. They recognized that nuclear reactors produced vast numbers of neutrinos through fission. A reactor offered a controlled, intense source, ideal for attempting the impossible. Their effort earned the name Project Poltergeist, a nod to the ghosts they were hunting. Raines and Cowan built massive tanks of water mixed with cadmium chloride, designed to capture faint bursts of gamma light created when a neutrino struck a proton. Such a collision was incredibly rare, even inside the overwhelming neutrino flux near a reactor. But after painstaking refinement and months of observation, the impossible happened. Small, unmistakable flashes began to appear, signals that matched the expected fingerprint of a neutrino interaction. For the first time in history, a particle, once dismissed as undetectable, had left its mark on the physical world. The neutrino was real, and with that revelation, physics exhaled. The conservation of energy had survived. Yet the discovery opened more doors than it closed. Now that the neutrino existed, its properties and its secrets demanded exploration. And the first great mystery would arrive from the sun itself. Neutrinos were on their way to Earth in unimaginable numbers, but 2/3 of them were missing. What happened to the sun's neutrinos? Why were they disappearing? And what did that mean for the laws of nature? This was the puzzle that would reshape our understanding of the neutrino forever. Project Poltergeist. By the middle of the 20th century, the neutrino had become physics' most stubborn riddle. It existed in equations, yet refused to appear in experiments. Physicists could describe what it should be, what it should do, even how it should behave, but no one had ever seen one. The ghost particle remained just that, a ghost. And then, for the first time, scientists developed the tools to hunt it. The breakthrough came not from the sun, nor cosmic rays, nor radioactive minerals buried underground, but from a relatively new invention of the atomic age, the nuclear reactor. Reactors were unlike any previous laboratory environment. They were powerful engines of fission, producing floods of antineutrinos, more than any natural source on Earth. If neutrinos were truly real, if they truly carried energy away in beta decay, then a reactor's core would release them in astronomical numbers. To two physicists, Frederick Raines and Clyde Cowan, this opportunity felt like staring into the ocean after a lifetime of watching single drops of water. If there was any place where a neutrino might finally collide with matter, it was here, in the heart of a man-made star. Their plan was bold, unconventional, and so ambitious that many doubted it was even worth attempting. They needed a detector capable of noticing something that almost never happens, a neutrino striking a proton. The result of such an impact would be extraordinarily subtle, a tiny burst of gamma light, invisible to the naked eye, lasting for a fraction of a second. Catching a neutrino was like waiting for a silent raindrop to hit a single grain of sand in a desert. But Raines and Cowan proceeded anyway. They constructed what would become known as Project Poltergeist, a name that captured both the eerie nature of the particle and the scientific audacity required to pursue it. The detector was housed near a nuclear reactor in South Carolina, shielded from cosmic rays by layers of earth and steel. It consisted of tanks filled with water laced with cadmium chloride, a mixture chosen for a very specific reason. When an anti-neutrino collided with a proton, the resulting reaction would produce a positron and a neutron, each leaving a faint yet detectable pair of signals. Two brief flashes separated by microseconds. This dual signal was the scientist's key. Countless other processes in nature could mimic a single flash of light, but two flashes, timed perfectly apart, indicated the signature of a neutrino interaction. It was a cosmic fingerprint. Rains and Cowan worked tirelessly, refining their equipment, improving background suppression, and developing statistical methods to distinguish real interactions from noise. Days passed, weeks, months. For most of that time, the detector remained silent. It was an instrument built to hear whispers in a storm. And then the impossible happened. Tiny pulses, paired, consistent, timed exactly as theory predicted, began appearing in the data. They were faint but undeniable. The neutrino, long considered undetectable, had interacted. The ghost particle had touched ordinary matter and left a trace. For the first time in history, a particle that did not respond to charge, that passed unbothered through planets, stars, and detectors, had revealed itself. The confirmation reshaped the landscape of physics. It validated Pauli's desperate idea from 2030. It restored faith in energy conservation. It provided a cornerstone for nuclear physics and laid the groundwork for particle detectors that would follow. The neutrino, once a theoretical abstraction, had become a real, tangible member of the subatomic world. But perhaps most importantly, this discovery marked the beginning of neutrino astronomy. If a reactor could produce detectable neutrinos, so could the universe. Distant stars, exploding supernovae, the fusion core of the sun. These became laboratories for the ghost particle. Each source offered new questions, new mysteries, new insights. Yet the next chapter would not be triumphant, it would be troubling, because when scientists turned their attention toward the sun, the largest natural source of neutrinos by far, they found something deeply unsettling. The sun was shining, burning, fusing, radiating exactly as stellar theory predicted, but its neutrinos were not arriving in the numbers they should. Only 1/3 of the expected neutrinos reached Earth. The rest were missing. Rains and Cowan had solved the problem of detection, but now the universe presented a new puzzle, one far stranger, one far more consequential. What happened to the sun's neutrinos? Where did they go? The answer would challenge the standard model, rewrite the identity of neutrinos, and reveal one of the most profound properties in all of particle physics: the sunlight that went missing. Deep beneath the Black Hills of South Dakota, in an abandoned gold mine nearly 1.5 kilometers below the surface, a strange experiment took shape. It was the 1960s, and physicist Raymond Davis Jr. had been granted permission to transform a cavernous underground chamber into one of the most unusual observatories ever conceived. Not a telescope for light, but a telescope for ghosts. Davis was not searching for ordinary starlight. He was searching for the ghost particles born in the heart of the sun. Every second, the sun unleashed a vast flood of neutrinos produced by nuclear fusion, the same reactions that generate heat and light. These neutrinos streamed outward, unhindered, passing through layers of plasma, out into space, and across the gulf between stars. And because they interacted so rarely with matter, they reached Earth carrying information straight from the solar core. If humans wanted to look inside a star, neutrinos were the only messengers capable of making the journey intact. The scale of Davis's ambition required something unconventional. He filled a massive underground tank with 100,000 gallons of chlorine-rich dry cleaning fluid. The idea was elegant but extremely difficult. Occasionally, a passing solar neutrino would strike a chlorine atom, transforming it into a rare isotope of argon. If Davis could extract and count those argon atoms, he could measure the number of neutrinos arriving from the sun. This was no ordinary experiment. To shield the detector from the constant rain of cosmic rays, it had to be buried deep underground. To detect something as elusive as a neutrino, the experiment had to wait months at a time for just a handful of transformed atoms. And to avoid contamination, the entire system had to be completely sealed, monitored, and refined. Yet despite the difficulty, Davis believed it would work. Solar theory was solid. Nuclear fusion in the sun's core should produce a predictable number of neutrinos. The home stake detector, if successful, would reveal a perfect match between the sun's predicted behavior and its actual neutrino output. But when Davis began collecting data, he found something profoundly wrong. Instead of the expected number of neutrinos, the detector recorded only 1/3. The sun was producing neutrinos, but 2/3 of them had vanished by the time they reached Earth. The star that powered our world appeared to be operating at a fraction of its predicted intensity. The result was alarming. If the sun was truly emitting fewer neutrinos, it meant the fusion reactions in its core were far weaker than theory suggested. That possibility was terrifying. The sun might be in a slow, silent decline. Some scientists worried that the discrepancy hinted at flaws in solar models themselves. Others suspected a mistake in the Homestake experiment, contamination, miscounting, or flawed assumptions. But Davis refined the detector repeatedly. He improved the purification systems, perfected the extraction process, minimized background noise, and recalibrated the counting methods. Yet every time he repeated the experiment, the same unsettling pattern emerged. 1/3 of the predicted neutrinos arrived, no matter how carefully the procedure was executed. The solar neutrino problem was born. For years, the scientific community debated its cause. The sun had been studied for centuries, from the behavior of sunspots to the oscillations on its surface. Its structure was considered one of the most well-understood objects in astrophysics. For it to produce only 1/3 of its expected neutrinos meant something was fundamentally missing from solar theory, nuclear physics, or both. Davis stood by his results, but he was alone in the darkness of that underground chamber, figuratively and literally. The detector remained buried far below the surface, isolated from the world, listening for ghosts that arrived far fewer than expected. There was, however, another possibility, a possibility almost no one wanted to consider because it implied something transformative. Perhaps the sun was producing all the neutrinos it should. Perhaps the missing ones were not truly missing at all. Perhaps they were changing into forms that the Homestake detector simply could not see. It was a radical idea, one that required neutrinos to be far stranger than anyone had imagined. Neutrinos, according to the standard model of particle physics, were supposed to be massless and unchanging. They were born as a specific type and remained that type forever. The Homestake detector was sensitive only to electron neutrinos, the flavor produced directly by the sun. If neutrinos were somehow changing identity on their journey, becoming muon or tau neutrinos, the Homestake tank would be blind to them. The missing neutrinos would not be gone. They would be hidden. This explanation seemed too exotic at the time, too removed from established physics. And yet, as more experiments appeared worldwide, the pattern remained the same. Solar neutrinos were consistently fewer than predicted. The truth, once uncovered, would shake the foundations of the standard model. The missing neutrinos were not disappearing, they were transforming. The discovery of neutrino oscillations. For decades, the mystery lingered like a quiet tension running beneath the surface of physics. The sun seemed to be sending fewer neutrinos than expected, and every new experiment, no matter how refined, echoed the same unsettling result. Something was happening to these particles between the core of the sun and the detectors on Earth. Something strange, something transformative, something that defied the rules physicists thought were unbreakable. If neutrinos were changing identity, it meant that the universe contained behaviors no theory had accounted for. It meant the standard model, the elegant framework describing all known particles and forces, was incomplete. The first hints came from unexpected corners. Underground laboratories in Japan, the Soviet Union, and later Canada began constructing new types of detectors, massive tanks of water, heavy water, or other transparent elements surrounded by arrays of sensors that could see the faintest flashes of Cherenkov light. These detectors weren't just looking for neutrinos, they were attempting to distinguish between different kinds of them, and slowly, patterns began to emerge. In the 1990s, scientists operating a vast underground detector deep within Japan's Kamioka Observatory made a breakthrough that shook the field. This instrument, a shimmering cathedral of pure water, monitored by thousands of photomultiplier tubes, was sensitive not only to electron neutrinos, but also to muon neutrinos. This broadened sensitivity allowed researchers to track neutrinos produced by cosmic rays striking Earth's atmosphere. If neutrinos behaved as theory predicted, the number of muon neutrinos passing down through the atmosphere should match the number passing upward through the Earth. But the detector saw something radically different. The neutrinos arriving from below, the ones that had traveled thousands of kilometers through the planet, were missing. Not fewer, missing. The implication was stunning. Neutrinos were altering themselves during their journey. Those produced in the upper atmosphere as muon neutrinos were arriving at the detector as something else entirely. They were changing flavor. Around the same time in Canada, another experiment took shape in the depths of an abandoned nickel mine. This one was built with a special purpose: to measure solar neutrinos in a way no previous detector could. Using heavy water, an extremely rare form of water containing deuterium, the experiment could see not only electron neutrinos, but also the total number of all neutrino flavors combined. What it found was decisive. The total number of neutrinos arriving from the Sun was exactly what solar models predicted. The Sun was functioning perfectly. The fusion processes powering its core were intact, steady, and as luminous as ever. The apparent deficit seen in earlier experiments wasn't due to a malfunctioning Sun. It was the neutrino. The detectors sensitive only to electron neutrinos saw just 1/3 because the other 2/3 had morphed into flavors they could not detect. Those neutrinos hadn't vanished, they had changed. This discovery carried an even more dramatic implication. For a neutrino to shift from one flavor to another, it had to possess mass, an almost impossibly tiny mass, far smaller than that of any known particle, but unmistakably real. This one revelation cracked open a new frontier. It meant the standard model, once believed to be a complete description of fundamental particles, was missing something essential. A particle predicted to be massless was in fact not massless at all. The very architecture of physics needed revision. Generations of assumptions had to be rewritten. Neutrino oscillation, the ability to shapeshift between electron, muon, and tau forms, became one of the most profound discoveries of modern science. It bridged astrophysics and particle physics. It explained decades of experimental tension, and it opened a doorway into questions that reached far beyond the Sun. Why do neutrinos have mass? What mechanism gives them this property when other particles gain mass through the Higgs field? And if neutrinos can change identity, what might they reveal about the early universe, where matter and antimatter fought for survival? Suddenly, these quiet particles, once dismissed as nearly irrelevant, held center stage in the search for answers about the universe itself. The mystery of the missing sunlight had evolved into a revelation that defied expectations. Neutrinos were not passive bystanders drifting through space. They were dynamic, fluid, and deeply woven into the fabric of cosmic evolution. Beams across continents. For most of the 20th century, neutrino detection meant looking deep underground, shielding delicate instruments from the constant rain of cosmic rays and radioactive noise. But by the late 1990s, it was becoming clear that the world needed something far more ambitious, something capable of catching particles that had traveled across the universe, not just across the Sun. The idea that took shape was audacious. Instead of building a detector, use the Earth itself as part of the detector. Find a place where matter is so clear, so undisturbed, that the faintest flash of light could travel for hundreds of meters without scattering. Then fill that place with a lattice of ultra-sensitive optical sensors and wait for a neutrino, just one, to collide with an atom and leave behind a streak of blue Cherenkov light. There was only one place on Earth that fit that description: the ancient glacial ice of Antarctica. The project that emerged from that vision became one of the most ambitious physics experiments ever attempted. Its construction required drilling more than 2 kilometers into the ice and lowering thousands of detectors into freshly melted shafts before the water refroze around them. Each module had to be sealed, autonomous, and resilient enough to survive pressures no machine had endured before. When completed, the observatory spanned a cubic kilometer, an entire continent's worth of frozen silence, transformed into a telescope that did not look up but looked through the planet. It was here, beneath the South Pole, that researchers began to detect neutrinos with energy so immense they defied categorization. These were not particles produced by the sun or by nuclear reactors. They were born in places where nature accelerates matter to unimaginable speeds. The hearts of quasars, the jets of blazars, the shock waves of stellar explosions, or collisions involving compact objects like neutron stars. Each detection was a postcard from somewhere far beyond the reach of ordinary astronomy. And yet, even these monumental energies were only the beginning. When the observatory recorded a single neutrino with an energy reaching tens of peta-electron volts, a scale so extreme it bordered on the theoretical, it forced the entire field to reconsider the limits of high-energy astrophysics. This particle had traveled an almost impossible distance, surviving intergalactic space, cosmic microwave background photons, and the turbulent magnetic fields of galaxies. It passed through the Earth as if the planet were a shadow. Only in the final fraction of a second did it collide with an atom in the ice and leave behind a faint trace of its passage. As these detections accumulated, a new picture of the universe began to emerge. Not a universe defined only by stars or galaxies, but one shaped by violent engines capable of accelerating particles to energies far beyond anything humanity could produce. A universe where neutrinos act as messengers from hidden realms, regions of such density, heat, and magnetic chaos that no other form of radiation can escape intact. But high-energy detections were only one side of the story. Across the globe, other observatories were turning vast bodies of water into listening posts for the same elusive particles. In the Mediterranean Sea, long vertical strings of photomultipliers swayed gently in the deep ocean, waiting for brief flashes of blue light. In Lake Baikal, beneath layers of winter ice, a similar array watched over the dark, cold water, listening for signals that could reveal new astrophysical sources. These detectors, all operating under different environmental conditions, formed a distributed network across the planet, a planetary-scale antenna tuned to the quietest signals the universe emits. And with every new installation came a stronger message. Neutrino astronomy was no longer a niche discipline. It was becoming one of the central pillars of multi-messenger astrophysics. Alongside gravitational waves and electromagnetic observatories, neutrino detectors were opening a new window, one that saw the cosmos not as a bright and visible canvas, but as a landscape filled with hidden accelerators and distant cataclysms. What made neutrinos so valuable was not just what they revealed, but what they ignored. They did not scatter like photons. They did not twist under magnetic fields like charged particles. They did not fade or lose direction as they crossed cosmic distances. They moved in straight lines, carrying the imprint of their birthplace with pristine clarity. And yet, as the detectors grew more sensitive, an unexpected problem began to surface. The very particles researchers relied on to illuminate the universe were also infiltrating experiments designed for a completely different purpose: dark matter searches buried deep underground. Neutrinos, once considered almost undetectable, were now becoming so abundant and unavoidable that they threatened to obscure the signal from the very particles physicists were trying to find. A new conflict was emerging, one between the search for the universe's most elusive known particle and the search for an entirely unknown one. And in laboratories beneath mountains and deserts, the two ghostly worlds were beginning to collide. The rise of gigantic neutrino observatories. By the late 1990s, neutrino research had reached a crossroads. Traditional underground detectors, massive caverns filled with ultra-pure water, heavy metals, or scintillating liquids had pushed their capabilities to the limit. They had revealed neutrino oscillations, measured flux from the sun, and captured signals from cosmic rays in Earth's upper atmosphere. Yet a new frontier was emerging, one that demanded technologies beyond anything physicists had previously attempted. If humanity wanted to observe neutrinos born in the most violent places in the universe, near black hole jets, exploding stars, or dense stellar remnants, it needed a detector far larger than any ever built and far quieter than the noisiest background interference that plagued Earth's surface. The breakthrough came in the form of an idea that felt almost unreal. Instead of constructing a conventional facility and shielding it from noise, the planet itself would supply the shielding. Instead of manufacturing a medium for particles to interact with, nature had already created one. Beneath Antarctica, untouched for tens of thousands of years, lay a staggering volume of crystal-clear glacial ice. It was dense enough to store the faintest luminous streak created by a neutrino interaction, yet transparent enough for that streak to travel hundreds of meters without scattering. If scientists could embed sensitive optical modules deep inside this frozen cathedral, the ice itself could become a detector, a vast three-dimensional volume where a single flash of blue Cherenkov light would signal a neutrino's silent arrival. The challenges were immense. Engineers needed to drill holes more than 2 kilometers deep, melting shafts through ancient ice layers that had remained undisturbed since long before human civilization. The sensors lowered into these shafts, spherical optical modules containing delicate photomultipliers, had to be rugged, autonomous, and capable of surviving the crushing pressure of the ice refreezing around them. Once sealed inside the glacier, they would remain frozen in place permanently, forming a massive lattice of electronic eyes tuned to detect the faintest hint of Cherenkov radiation. When the final module was lowered and the construction complete, the observatory spanned a cubic kilometer in volume, transforming a frozen continent into one of the largest scientific instruments ever conceived. Soon after activation, the observatory started detecting neutrinos of increasing energy. Some originated from cosmic rays, striking Earth's atmosphere, producing showers of secondary particles. Others came from the sun, carrying information from the heart of solar fusion. But then the detections reached a level no one had anticipated. Neutrinos with energies tens of thousands of times higher than those produced by particle accelerators on Earth. These neutrinos carved faint, geometric traces through the ice, signatures of violent astrophysical events far beyond the reach of conventional telescopes. Their origin points lay in extreme environments, close to supermassive black holes, within the shock fronts of exploding stars, or along the magnetic highways where blazar jets hurled matter across intergalactic distances. One particle in particular captured the attention of the scientific world. With an energy reaching into the tens of peta-electron volts, it represented an astrophysical process so powerful that no human-made machine could begin to replicate it. The neutrino had almost certainly traveled unbent and unscattered across galaxies, threading its way through cosmic microwave background photons and turbulent magnetic fields with complete indifference. It sliced through Earth as if the planet were barely there. Only in the last instance of its journey did it interact with an atom in the Antarctic ice, producing a crisp blue trail that revealed both its energy and its direction of origin. In a single detection, it demonstrated what made neutrinos extraordinary. They carry the story of their birthplace without distortion. As the South Pole detector continued its work, other observatories joined the global effort. In the deep Mediterranean Sea, strings of sensors anchored to the seafloor watched the dark water for sudden flashes of light. In Lake Baikal, one of Earth's oldest and deepest lakes, another array of optical modules listened for Cherenkov bursts passing through fresh water older than most geological formations. Each site, shaped by its environment, added a crucial piece to the planetary listening network. Together, they formed a global mosaic of detectors tuned to an invisible universe that could not be probed by light alone. This was the dawn of multi-messenger astronomy. Neutrinos carried information that photons could not. They escaped from environments so dense and chaotic that light became trapped. They ignored magnetic fields and traveled in straight lines across cosmic distances. They arrived from places where matter spiraled around black hole, where neutron stars collided, or where shock fronts accelerated particles to near light speed. And unlike electromagnetic signals, neutrinos did not fade or distort. They delivered a pristine message encoded in their direction energy, and timing. Yet with each improvement in sensitivity, an unexpected challenge began to appear. The more successful neutrino observatories became, the more difficult they made life for another field of physics, dark matter research. Detectors buried deep underground, designed to catch particles far more elusive than neutrino, began to record faint signals that were not dark matter at all. They were neutrinos sneaking into experiments through the Earth itself. What had once been considered the ultimate undetectable particle was now everywhere, drifting through apparatus designed for something even stranger, contaminating measurements and complicating the search for the universe's missing mass. The irony was unmistakable. The very particles that had eluded detection for decades were now becoming so unavoidable that scientists had to devise new strategies to filter them out. Neutrinos, once quiet bystanders, were now loud enough to drown out whispers from the dark sector. In the span of a century, physics had gone from not knowing neutrinos existed to building planetary-scale machines to capture them, unraveling cosmic secrets while simultaneously revealing how profoundly these tiny particles govern the landscape of high-energy astrophysics. The hunt for cosmic neutrinos. By the dawn of the 21st century, neutrino science was no longer confined to laboratory puzzles or solar mysteries. Researchers were beginning to realize that these ghost-like particles could be the universe's most powerful messengers, capable of escaping environments where photons were trapped, capable of preserving their direction over cosmic distances, and capable of carrying information from places where matter is torn apart at relativistic speeds. The challenge was no longer simply detecting neutrinos, it was detecting the right ones, the particles forged in astrophysical engines so violent that only neutrinos could emerge unscathed. Cosmic neutrinos differ dramatically from those produced in the Sun or Earth's atmosphere. Their energies are staggering, sometimes reaching into the peta-electron-volt range, far beyond anything achieved in terrestrial accelerators. These particles originate in the most extreme places known to science, within the jets of active galactic nuclei, the shock fronts of stellar explosions, and regions where magnetic fields twist violently around compact objects. When one of these high-energy neutrinos crashes into a detector, it leaves a distinctive imprint, a sharply defined track or cascade pattern that hints at its extraordinary origin. As observatories around the world matured, they began to detect these signatures more frequently. Antarctic ice recorded long, luminous streaks created by neutrinos that had passed through thousands of kilometers of Earth before interacting. Deep-sea detectors captured spherical bursts of blue light, expanding outward like silent explosions beneath the waves. Each detection represented the final moment of a particle's journey that had begun millions of years earlier, in a place far removed from anything humanity had ever observed directly. These neutrinos opened a new frontier in astrophysics. Unlike photons, which scatter and lose information as they travel through dense regions, neutrinos preserve a clean memory of the processes that created them. They trace straight lines across galaxies, carrying both direction and energy as a signature of their birthplace. When a detector registered one of these particles, it was not simply measuring an interaction, it was reconstructing the final chapter of a cosmic story written long before Earth existed. Certain sources became prime suspects for producing these extreme particles. Blazars, with their jets aligned toward Earth, were natural accelerators capable of generating collisions powerful enough to produce neutrinos of extraordinary energy. Gamma-ray bursts, fleeting explosions marking the collapse of massive stars, or the merger of compact objects were another contender. Even the turbulent regions around supermassive black holes, where plasma spirals inward at nearly light speed, offered conditions extreme enough to forge high-energy neutrinos. But identifying a specific astrophysical source required more than a single detection. It demanded correlation, matching the arrival of a neutrino with a simultaneous signal elsewhere in the electromagnetic or gravitational spectrum. This need for coordination led to the rise of multi-messenger astronomy, a field that united observatories across the planet. When a candidate neutrino arrived, telescopes scanned the sky. X-ray satellites pivoted their mirrors. Gamma-ray observatories combed through their data. Each instrument searched for a flare, a burst, or an anomaly coinciding with the neutrino's arrival time and direction. This collaborative approach revealed its power when a high-energy neutrino was traced back to a blazar undergoing a violent flare. For the first time, researchers could point to a specific object in the sky and say, with confidence, this is where that particle came from. It was a watershed moment, proving that neutrinos could be used not only to detect cosmic accelerators, but to map them. Yet even as these successes accumulated, new complexities emerged. The universe is full of background neutrinos from countless processes: solar fusion, atmospheric interactions, radioactive decay, even relic neutrinos from the first seconds after the Big Bang. Distinguishing the rare astrophysical signals from this constant background required techniques that pushed statistical methods to their limits. Every detection had to be scrutinized, every pulse analyzed, every track reconstructed with precision, measured in nanoseconds. The hunt for cosmic neutrinos became an intricate dance between signal and noise. But with each new detection, physicists gained more insight into the mechanisms that shape galaxies and power the universe's most energetic events. Neutrinos provided glimpses into regions no telescope could penetrate, revealing processes that operated beyond the reach of electromagnetic observation. And as detectors grew larger and more sophisticated, the scope of the hunt expanded. No longer limited to identifying single sources, researchers began searching for patterns, clusters of neutrino events that might indicate hidden accelerators or undiscovered astrophysical phenomena. The invisible universe was gradually becoming visible, not through light, but through particles that slipped silently across the cosmos. The pursuit of cosmic neutrinos was no longer a fringe effort. It had transformed into a core pillar of modern astrophysics, a discipline that merged particle physics with cosmology and demanded instruments as large as mountains and as quiet as the deep sea. Neutrinos versus dark matter. As neutrino observatories grew more powerful and precise, a strange inversion began to unfold. The particle that once haunted physicists by its absence started showing up everywhere. For researchers chasing dark matter, this was not a blessing, it was a problem. Dark matter detectors are built with almost obsessive care. They sit buried under mountains or deep underground, shielded from cosmic rays by layers of rock. Their walls are made of ultra-clean material. Their target volumes, often liquid xenon, argon, or germanium, are cooled and isolated so that any interaction inside might be the fingerprint of an unknown particle passing through. For years, the hope was to see the faint nudge of a weakly interacting massive particle, a WIMP, colliding with an atomic nucleus and leaving behind a tiny, measurable recoil. But the universe had other plans. Neutrinos, which had long been considered a background too small to worry about, gradually became a fundamental limitation. Solar neutrinos streamed constantly through the Earth, through rock, and straight into dark matter experiments. Atmospheric neutrinos produced by cosmic rays did the same. As detectors became more sensitive, they started to pick up these interactions. The ghost particles, once the hardest thing to see, turned into a kind of glowing haze that was impossible to turn off. Physicists began to speak of a neutrino flaw. It is not a physical barrier, but a practical one, a level of sensitivity beyond which dark matter signals are entangled with neutrino interactions so thoroughly that separating them becomes almost impossible. At that point, the universe is no longer quiet. It is filled with a constant, irreducible murmur of neutrino events that mimic the very signals dark matter experiments are trying to isolate. The irony is sharp. To discover dark matter, scientists had to master the art of detecting weak, rare interactions in pristine detectors. In doing so, they became so good at this that the universe's faint neutrino background now interferes with the search. The ghost that once hid in the shadows has stepped into the spotlight and refuses to leave. Yet this annoyance comes with unexpected opportunity. The same physics that makes neutrinos a nuisance for dark matter experiments also unlocks a new way to study them. One of the most intriguing processes is coherent elastic neutrino nucleus scattering, often shortened to CEVNS. In this effect, a low-energy neutrino interacts not with individual protons or neutrons, but with the entire nucleus as a whole. The nucleus recoils ever so slightly, shifting its momentum in a way that can be measured if the detector is sensitive enough. This phenomenon was predicted in the 1970s, but it remained out of reach for decades. The recoil energies are incredibly small, and only recently have detectors become precise enough to see them. The first clear confirmation came from an accelerator experiment, but the latest breakthrough pushes the boundary further, demonstrating CE-V-NS at a nuclear reactor using a detector so compact it could be mistaken for lab equipment rather than a monumental observatory. At the Liebstadt nuclear plant in Switzerland, the CONUS Plus experiment uses germanium semiconductor detectors totaling only about 3 kilograms in mass. Placed a little more than 20 meters from the reactor core, it is bathed in a torrent of anti-neutrinos. Over months of operation, researchers teased out a tiny excess of signal, hundreds of events, above the background, matching predictions for coherent elastic scattering. In a world used to detectors the size of buildings, the idea that a device the mass of a lunchbox can weigh neutrinos by the collective twitch of atomic nuclei is almost surreal. This achievement marks a turning point. The same process that creates confusion in dark matter searches now becomes a tool. Small CEVNS detectors could one day monitor reactor output, track fissile content non-invasively, or probe subtle deviations from the standard model. In the same breath, they remind physicists that neutrinos are no longer just an exotic curiosity. They are an unavoidable part of the experimental environment. In high-precision physics, neutrinos now play both roles at once. They are a signal and a background, a probe and an obstacle, a tool for testing fundamental theories, and a fog that limits how far those tests can go. For dark matter researchers, the message is clear. Any future experiment must be designed not just to see through rock and shield against radiation, but to live in a universe where ghost particles are no longer rare visitors. They are everywhere, all the time, and they are impossible to ignore. When neutrinos reveal their true identities, neutrinos were once assumed to be simple particles, light, neutral, and mostly irrelevant to the larger tapestry of the cosmos. But as detectors grew stronger and accelerators more precise, it became clear that these particles were anything but simple. They were shapeshifters. Each one could begin its journey as one flavor and end as another, transforming rhythmically as it traveled. This behavior, known as oscillation, became one of the greatest clues to understanding why the universe is made of matter at all. To study oscillations with precision, physicists built experiments that spanned continents. Quite literally, these were called long baseline neutrino experiments, designed around a surprisingly elegant idea: create a beam of neutrinos in one location, then detect it hundreds of kilometers away after the particles have had time to evolve. Two of the most ambitious long baseline experiments ever built now stand as counterparts on opposite sides of the globe. In Japan, the T2K experiment sends a beam of neutrinos from the JPARC accelerator toward the Super Kamiokande detector nearly 300 kilometers away. In the United States, NOVA launches its own beam from Fermilab in Illinois toward a massive detector in northern Minnesota, a journey of more than 800 kilometers. Both experiments observe how muon neutrinos morph into electron neutrinos along the way. Both measure how neutrinos differ from their antimatter partners, and both are hunting the same elusive prize: the moment when neutrinos reveal whether they treat matter and antimatter differently. One of the possible keys to understanding why galaxies, stars, planets, and people exist. Each experiment on its own has immense power, but together they create something more. T2K and NOVA do not operate at the same energy. Their beams travel different distances and pass through different densities of Earth. Their detectors use different technologies, geometries, and analysis methods. In most fields, such differences would make collaboration complicated, even counterproductive. In neutrino physics, those differences are gold. They allow each experiment to highlight the other's blind spots, to test the same physics from two angles, and to cross-examine nature with complementary strengths. For years, combining their data seemed like a dream that would never materialize. The datasets were enormous. The statistical frameworks were different. Even the ways the two collaborations defined uncertainties did not match. But the physics demanded unity. If neutrinos truly held the key to breaking the symmetry between matter and antimatter, no experiment acting alone could unveil that truth. So, the collaborations decided to do something rare in high-energy physics: merge their analyses into one. Researchers spent years aligning methods, standardizing models, and painstakingly verifying every assumption. They checked detector responses, compared oscillation frameworks, and agreed on common statistical treatments. By the time the combined dataset was complete, it represented more than a decade of T2K results and 8 years of nova measurements, an achievement built not only on engineering and mathematics, but on cooperation across continents. The combined analysis pushed the precision of oscillation parameters into territory previously unreachable. It offered the sharpest view yet of how muon neutrinos convert into electron neutrinos, and it brought physicists closer than ever to answering one of the most fundamental questions in cosmology: the neutrino mass ordering. Which neutrino is the lightest? Which is the heaviest? How exactly do the three mass states arrange themselves in the subatomic hierarchy? Two possibilities remain. In the normal ordering, the lightest mass state aligns primarily with the electron neutrino. In the inverted ordering, the electron-type mass state sits at the top, with the other two below. The distinction seems small, almost trivial in human terms, but in the language of the early universe, it could be the difference between annihilation and survival. The combined T2K and nova results pushed the evidence slightly toward normal ordering, but not conclusively. They narrowed the possibilities. They sharpened the landscape, but the universe has not yet revealed its final verdict. The same analysis also probed the phenomenon that could rewrite cosmology itself: charge parity violation, or CP violation. If neutrinos behave differently from antineutrinos, even subtly, it would mean the universe has a preferred bias toward matter. That bias, however small, could echo back to the first split seconds after the Big Bang, explaining why matter didn't vanish into oblivion when antimatter met it head-on. The combined dataset hints at possible asymmetry, but the evidence is still shy of certainty. The signal is there, just beyond reach, waiting for the next generation of experiments to clarify it. The coming giants. As impressive as the achievements of T2K and NOVA are, they represent only the opening chapters of a story that is now accelerating toward a new frontier. Physicists have tasted precision. They have glimpsed the edges of an asymmetry that may explain why the universe is filled with matter rather than empty darkness. They have identified hints, just hints, of how neutrinos might be arranged in their mass hierarchy. But hints are not enough. To solve the neutrino mystery, the world needs detectors of a scale and ambition far beyond anything built before. And so, two monumental experiments are rising on the global stage, massive, multi-generational undertakings that will push neutrino research into a new era. Their names carry weight even outside physics. Dune in the United States and Hyper Kamiokande in Japan. Together, they represent humanity's strongest attempt yet to uncover the hidden rules guiding matter, antimatter, and the universe itself. Dune, the deep underground neutrino experiment, is an engineering feat bordering on the surreal. It is built on a simple idea taken to a staggering extreme: fire an intense beam of neutrinos from Fermilab outside Chicago and aim it straight through the Earth toward a detector buried 1,400 meters underground in South Dakota. No tunnel is needed. Neutrinos ignore the planet's crust, mantle, and core as though they are not there. They travel in straight lines, unhindered, making the Earth itself part of the experimental setup. The beam originates from the Proton Improvement Plan 2 Accelerator, a machine built to deliver the most intense neutrino beam ever produced. The protons smash into a graphite target, creating showers of unstable particles that quickly decay into muon neutrinos. These neutrinos then begin their journey westward, traveling 1,300 kilometers in a blink of an eye. Just 500 meters from their birthplace, the neutrinos pass through Dune's near detector, a movable, highly instrumented system designed to measure the beam before oscillations occur. This establishes the baseline, the original identity of the neutrinos. Only then can physicists meaningfully compare what arrives in South Dakota with what was sent from Illinois. The FAR detector complex, housed in 3 enormous caverns carved out of the rock beneath the Sanford Underground Research Facility, will eventually contain almost 70,000 tons of liquid argon. The detectors will stand 5 stories tall, each one like a cathedral of frozen light. When a neutrino interacts inside, it triggers a cascade of electrons that drift through the liquid and are captured by precise arrays of sensors. These sensors reconstruct the interaction in 3 dimensions with astonishing clarity, almost as if someone paused subatomic physics and photographed it frame by frame. Dune's mission is vast. It aims to determine whether neutrinos and antineutrinos behave differently. It intends to measure the mass ordering with unprecedented precision. It will search for sterile neutrinos, investigate supernova explosions in real time, and attempt to detect hypothetical processes that go beyond the standard model. For the first time, humanity will have an instrument capable of seeing neutrinos with the detail required to test whether the laws of physics are symmetric or biased in favor of matter. On the other side of the Pacific, Japan is constructing its own titan, Hyper Kamiokande, the successor to Super Kamiokande, the detector that helped reveal neutrino oscillations in the 1990s. Hyper K takes the Super K philosophy and magnifies it. It is a cylindrical cavern, 100 meters tall and 100 meters wide, filled with ultra-pure water and lined with layers of photodetectors that will number in the tens of thousands. These sensors are tuned to record Cherenkov light, the ghostly blue glow produced when charged particles move faster than light can travel through water. Japan's upgraded accelerator complex will send a neutrino beam toward Hyper K, allowing it to perform oscillation studies with far greater precision than ever before. Hyper K's immense volume ensures sensitivity to an enormous range of energies and interaction types. It will also act as one of the most sensitive supernova detectors in the world, capable of capturing neutrino bursts from collapsing stars anywhere in the Milky Way. While Dune uses liquid argon's ability to reconstruct every detail of a neutrino event, Hyper K leverages the sheer scale and clarity of water Cherenkov detection. The contrast between the 2 experiments is deliberate. Together, they form a global approach. 2 different technologies, 2 different baselines, 2 different strategies to converge on the same fundamental answers. Both experiments are expected to begin operations in the early 2030s. Their timelines stretch across decades. Their successes depend on thousands of scientists, engineers, and technicians worldwide, and their promises are profound. If neutrinos do violate charge parity symmetry, Dune and Hyper K will be the experiments that reveal it. If the mass ordering is normal or inverted, they will provide clarity. If sterile neutrinos exist, they stand a chance of catching them. And if supernovae erupt in our cosmic neighborhood, these detectors will witness the explosion from inside the star through the messenger particles that escape before light itself can break free. In a sense, Dune and Hyper K are not just experiments. They are monuments to curiosity, tools of a civilization determined to uncover its origin. They represent humanity's decision to chase a particle so elusive that it passes through entire planets without slowing, yet so fundamental that it may explain why anything exists at all. When neutrinos first appeared in Pauli's equations, they were a desperate solution to an impossible problem. Today, They are at the heart of the most ambitious physics projects ever conceived. What comes next will depend on what these giants reveal when the first beams fire and the first events flash across their detectors, signals from particles that have crossed Earth untouched, only to leave their mark at last. The neutrino fog. Long before the first atoms formed, before the first galaxies spiraled into being, before light itself could move freely through space, the universe was filled with neutrino. They were among the very first particles to decouple from the primordial plasma, escaping the dense, hot fog of the early cosmos roughly 1 second after the Big Bang. These neutrinos have been traveling ever since, untouched, unaltered, unscattered. They are relics of cosmic childhood, the oldest messengers in existence. Scientists call this unseen ocean the cosmic neutrino background. If the cosmic microwave background, the faint radio glow discovered in the 1960s, is the photographic imprint of the universe at 380,000 years old, then the cosmic neutrino background is the echo of the universe at just 1 second old. Nothing else carries information from that era. Photons cannot. Matter did not yet exist in stable form. Gravity waves help, but even they do not probe that precise moment. Only neutrinos. Yet despite the fact that trillions of relic neutrinos pass through every person every second, they remain undetected. Their energies are unbelievably low, so low that no existing detector can register their presence. They are, quite literally, the faintest signal the universe has ever produced. Even so, they influence everything. Their collective mass affects the growth of cosmic structure. Their density shapes the expansion of the universe. Their behavior sets the stage for how matter later arranged into stars, galaxies, and clusters. They form a background so pervasive it quietly shapes the cosmos without ever revealing itself. The only reason we know relic neutrinos must exist is because the mathematics of the Big Bang demands them. Without these early neutrinos, the universe's elemental abundances would be wrong. The rate of expansion would be wrong. The cosmic microwave background would have the wrong structure. The relic neutrinos are woven into the fabric of cosmology, not as a theory to be debated, but as a requirement for the universe to make sense. Detecting them, however, is one of the greatest experimental challenges ever conceived. The energies involved are measured in the microelectron volt range, far below the threshold of conventional neutrino detectors. And unlike high-energy neutrinos from supernovae or blazars, these relic particles barely nudge matter at all. It is like trying to detect the impact of a single grain of dust falling on an entire continent. Still, scientists have developed bold ideas. One proposal involves using tritium, a radioactive isotope of hydrogen, whose beta decay spectrum could subtly shift if a relic neutrino interacted with one of its atoms. Another visionary design suggests embedding tritium into superconducting materials to detect the minuscule changes in energy caused by the neutrino's arrival. The most ambitious concepts involve using enormous volumes of ultra-cold atomic gases or advanced quantum sensors capable of feeling the faint tug of these ancient particles. If any experiment succeeds, it would mark a monumental moment in physics. It would be akin to hearing the heartbeat of the newborn universe. But relic neutrinos are only one piece of the cosmic fog. There are other neutrino backgrounds as well, each with its own origin, each overlapping the others like faint layers of a cosmic watercolor. There is the solar neutrino background, produced in the steady nuclear burning of the sun. There is the geoneutrino background, emitted from radioactive decay deep within Earth's interior. There is the atmospheric neutrino background, created when cosmic rays strike the upper atmosphere. And there is the supernova neutrino background, a diffuse wash of particles from every star that has collapsed in the history of the cosmos. This last one, often called the DSNB, the diffuse supernova neutrino background, is particularly fascinating. Each time a massive star ends its life in a supernova, it releases an enormous burst of neutrinos. Not just a few, but on the order of 10 to the power of 58. Almost all of them escape immediately during the core collapse. They leave the galaxy, drift into intergalactic space, and eventually pass through detectors on Earth thousands, millions, or even billions of years later. Individually, these neutrinos are faint, barely noticeable events, but integrated over all cosmic time, they form a whispering chorus, subtle, persistent, and rich with information about the life cycle of stars. Detecting the DSNB is within reach. Super Kamiokande is already on the threshold. DUNE, Hyper Kamiokande, and future megaton-scale detectors may finally observe it, transforming what is currently a theoretical background into a measurable fingerprint of cosmic history. But the relic neutrino background, the oldest, faintest, and most elusive of them all, remains beyond current technology. It is the final frontier of neutrino astronomy, a signal so ancient it predates light itself, yet scientists remain undeterred. The same optimism that drove the detection of solar neutrinos, atmospheric neutrinos, blazar neutrinos, and cosmic accelerators is now directed toward these primordial ghosts. And the motivation is simple. If we can detect relic neutrinos, we will not merely observe the early universe, we will touch it. What follows next is the realm where neutrinos intersect with gravitational waves, pulsars, and the vast machinery of multi-messenger astronomy, a revolution in how we observe the cosmos, listening to the universe through time. Long before neutrinos became the universe's ghostly messengers, another silent phenomenon rippled across the cosmos: gravitational waves. Predicted in the early 20th century, these waves are distortions in space and time themselves, subtle tremors produced whenever massive objects accelerate or collide. For decades, they existed only on paper, a prediction of general relativity so faint that detecting them seemed almost impossible. That changed in 2015, when a pair of black holes merged over 1 billion light-years away. As their gravitational waves passed through Earth, two enormous interferometers, LIGO, felt the slightest stretching and squeezing of space, a distortion smaller than the width of a proton. It was the first direct detection of gravitational waves, and with it, a new era of astronomy began. But gravitational waves come in many frequencies. LIGO and Virgo detect the high-frequency signals produced by black holes and neutron stars spiraling rapidly toward collision. Beneath this range lies a deeper hum, longer, slower, and subtler. These low-frequency waves are produced by titanic structures, supermassive black holes, tens of millions of times the mass of our Sun orbiting one another in the centers of merging galaxies. No Earth-based interferometer can detect waves this slow. Their wavelengths can stretch across light years. To perceive them, scientists needed a detector the size of the Milky Way itself, so they built one using pulsar. Pulsars are the corpses of massive stars, neutron stars that spin with relentless precision. With each rotation, they send out beams of electromagnetic radiation like cosmic lighthouses. Some spin hundreds of times per second. Their regularity rivals atomic clocks, drifting by no more than a few hundred nanoseconds over years. This consistency makes them perfect reference points for detecting distortions in space-time. Imagine dozens of these cosmic clocks scattered across the galaxy. Now, imagine monitoring the arrival times of their radio pulses with extraordinary precision. If space-time stretches or contracts as gravitational waves pass through the galaxy, even by an amount too small to detect with terrestrial instruments, the pulses from these neutron stars will shift ever so slightly, not randomly, but in a pattern, a correlated timing distortion sweeping across the sky. This approach forms a pulsar timing array, or PTA. It is a detector not built of mirrors or lasers, but of stars and space itself. Multiple international collaborations now operate PTAs: Nanograv in North America, the European PTA, the Parkes Pulsar Timing Array in Australia, and others spanning Asia and Africa. Together, they monitor dozens of millisecond pulsars, creating a galaxy-scale gravitational wave observatory. In 2023, a result emerged that shook theoretical physics. After years of analysis, Nanograv and its global partners announced evidence of a stochastic gravitational wave background, a diffuse hum washing through the galaxy, produced backed by a population of supermassive black hole binaries spread across cosmic time. Unlike the dramatic chirps detected by LIGO, this background is constant, ancient, and everywhere. It's not a single event, but a symphony of distant mergers, each too faint individually to detect, yet together forming a low-frequency cosmic vibration that resonates through the galaxy. For the first time, humanity was not just observing gravitational waves. We were listening to the universe breathing. But pulsars offer something more than gravitational wave detection. Their extreme densities, magnetic fields, and rapid rotations allow researchers to probe physics far beyond the laboratory scale. Some neutron stars emit beams with such precision that their signals can map distortions caused by interstellar plasma, variations in Earth's orbit, and even changes in planetary atmosphere. Others surprise us with glitches, sudden jumps in rotation rate that hint at exotic physics inside their superdense cores, possibly involving quark matter or nuclear pasta. And as PTAS grow, their ability to detect correlated timing patterns will increase. A larger pulsar network means finer resolution, higher sensitivity, and the potential to resolve individual supermassive black hole binaries. Eventually, PTAS may even pinpoint their positions in the sky, transforming gravitational wave astronomy from a statistical science into one with identifiable sources. The galaxy-wide detector is no longer a metaphor. It is a functioning scientific instrument, engineered not by human hands, but by the universe itself. The union of pulsar timing, neutrino astronomy, and gravitational wave detection marks the dawn of multi-messenger astrophysics. Each messenger, light, particles, and the bending of space reveals a different facet of cosmic events. Together, they transform our understanding of everything from stellar death to galaxy formation. Yet multi-messenger astronomy is not only about large-scale structures and distant black hole, it also intersects with the mysteries unfolding inside neutron stars themselves, objects whose interiors remain among the most exotic environments in existence. That leads us to our next journey, a descent into the hearts of neutron stars, where gravity crushes matter into states unknown on Earth, and where their collisions reshape the cosmic landscape, forging of the universe's heaviest elements. To understand the drama of a neutron star collision, it helps to remember the violence that created neutron stars in the first place. A massive star burns brightly for millions of years, fusing hydrogen into helium, helium into heavier elements, and pushing back against gravity with the pressure of nuclear fire. But when the fuel is gone, when iron builds up in the core and fusion can go no further, the balance breaks. Gravity wins. In less than a second, the core collapses. Electrons and protons merge into neutrons. The matter crushes into a single sphere barely 20 kilometers across. The outer layers rebound, erupting in a supernova bright enough to outshine an entire galaxy. What remains is one of the densest objects in the universe, a neutron star. A teaspoon of its material would outweigh mountains. A magnetic field billions of times stronger than Earth's wraps its surface, and many neutron stars spin so fast they complete hundreds of rotations per second. These extreme environments alone make neutron stars fascinating, but the real cosmic spectacle begins when two of them orbit each other. Over millions of years, their mutual gravity draws them together. They spiral inward, their motion releasing energy in the form of gravitational wave. By the final minutes of their lives, their orbits accelerate so rapidly that the fabric of space-time twists with each revolution. And then, collision. When two neutron stars merge, the event is among the most catastrophic transformations known. The combined mass overwhelms neutron degeneracy pressure, the force that kept each star intact. In a fraction of a moment, the matter inside is heated, compressed, and torn apart. Gravitational waves roar outward, carrying detailed signatures of the star's densities and internal structure. Light bursts into existence seconds later, marking a new kind of cosmic explosion called a kilonova. Unlike a supernova, a kilonova is driven by neutron-rich material flung into space. As these dense fragments expand and cool, they undergo rapid neutron capture, the R process, which builds the universe's heaviest elements. Gold, platinum, uranium, and rare earth metals all emerge from this crucible, condensed out of the violent nuclear storm. Every ring on a finger, every platinum circuit, every precious metal mined from Earth owes its existence to events like these. Human history has been shaped by elements forged in collisions between dead stars. For decades, astronomers suspected neutron star mergers were responsible for our process elements, but they had no proof. That changed in 2017, when a gravitational wave signal named GW170817 swept through detectors. Its pattern was unmistakable: two neutron stars spiraling together. Just seconds later, space telescopes captured a flash of light from the same region of the sky. For the first time, gravitational waves and electromagnetic radiation revealed the same event. Observatories around the world mobilized. They watched the kilonova evolve in real time as its color shifted from blue to red, revealing heavy elements condensing from the debris. This single cosmic disaster provided more answers in 1 week than decades of theory had produced. The lesson was clear: neutron stars are not just exotic remnants. They are factories for the elements that make planets, technology, and life possible. Yet the collision raises deeper questions. What truly lies inside a neutron star? The densities inside their cores may surpass anything possible in laboratories. Matter could exist not as neutrons, but as quark soup, or even as strange matter, where up, down, and strange quarks mingle freely. Some theorists propose that the transition between neutron-rich matter and quark matter might occur during the collision, briefly exposing the universe to conditions reminiscent of the first microseconds after the Big Bang. These mergers also push gravitational wave detectors to their limits. The waveforms encode the deformability of neutron stars, allowing scientists to map their internal stiffness or softness. Each detection brings us a step closer to understanding exotic states of matter that cannot be reproduced on Earth. Neutron star collisions also contribute to the neutrino landscape. During the merger, vast numbers of neutrinos flood out, carrying away energy and influencing how heavy elements assemble. Models of kilonova explosions now rely heavily on neutrino physics, oscillations, interactions, and flavor transformations to understand exactly which elements emerge and in what quantities. In all these ways, neutron stars lie at the crossroads of modern astrophysics. They connect nuclear physics, gravitational waves, neutrinos, and cosmology into one unified story. And yet, the end of this chain leads to an even deeper mystery: the nature of black holes themselves. The regions where gravity grows so intense that even space and time bend inward. The places where singularities form, or perhaps do not form at all. That's it for today. Let us know your thoughts in the comments down below. Don't forget to like and subscribe for more space content.